Okay, my name is Natalie and I want to discuss about question 1. Based on the chromatogram data provided, here is the assessment of column 1 and column 2. To determine which column is more efficient for component B, calculate the number of theoretical flags using the peak width at the base and retention time. I effectively correspond to narrow peak and a higher value of n. By using the given formula and the data given, just substitute it and we'll get the column 1 and value is 1111 flags, and for column 2 the n value is 381 flags. So the recommendation is column 1 is significantly more efficient. It provided approximately 1111 theoretical flags compared to only 381 for column 2. A higher end value indicates less band broadening, resulting in shorter peak and better detection limits. Okay, and then for the peak resolution, as value, to determine if the peak are well resolved, calculate the resolution between component A and component B for both colors. Okay, by the analysis of column 1, the given data, and just substitute it to the formula, and you will get RS value for column 1 is equal to 1.82, and for analysis of column 2, the RS value is equal to 0.89. So the resolution status, column 1, the peak are well resolved in chromatography and RS value of more than 1.5 is required to achieve baseline resolution. Complete separation with less than 1% overlap. Since 1.8 to more than 1.5, baseline resolution has been achieved. And for column 2, the peaks are not well resolved because an RS value less than 1 detects significantly peak overlap, making accurate quantification difficult. So, in conclusion, I strongly recommend utilizing column 1 for this separation. It demonstrates superior column efficiency for component B because of the higher let's count and the active personal resolution compared to column 2 which try to separate the analyte effectively. Okay, that's all for me.
The illusion order directly reflects the decreasing of polarity and increasing the hydrophobicity of the compound. The stronger the hydrophobic interaction with the C18 stationary phase, the longer the retention time. There are three compounds. Compound number 1 is anisole or methoxybenzene. Anisole contain a methoxy group or CH3 which is moderately polar. Although it increases the purity compared to benzene, the purity anisole still retains some hydrophobic character due to the aromatic ring. Therefore, anisole show intermediate retention and elutes after the nitrobenzene but before the benzene. Compound number 2, benzene. Benzene has no polar substituents and is entirely non-polar. It interacts most strongly with the hydrophobic C-acid stationary phase through the van der Waals interaction. Consequently, benzene is retained the longest in the column and elutes first. Compound number 3 is a nitrobenzene that contains a nitro group NO2 which is a strongly electron withdrawing the highly polar. This increases the overall polarity of the molecule and reduces its hydrophobic interaction with the non-polar C18 stationary phase. As a result, nitrobenzene spend more time in the polar mobile phase and elute first. So, compound number 3 is a first peak, compound number 1 is second peak, and the compound number 2 is a third peak.
Moving on to question 3, the question wants us to identify functional groups in the following FTIR spectra for the given chemical structure. For diagram 1, peak A corresponds to alkyl groups attached to sp3 hybridized carbons appearing in the region of 2850 to 2950 cm to the power of -1. This absorption is characteristic of alkane functional groups and arises from CH stretching vibration of CH3 and CH2 units, confirming the presence of alkyl groups in the molecule. Peak B observed at 1660 cm to the power of -1 within the range of 1640 to 1680 cm to the power of -1 indicates a carbon-carbon double bond and is assigned to an alkene functional group. This band results from the stretching vibration of the C double bond C bond and is typically more intense in cis alkenes due to reduced molecular symmetry and a greater change in dipole moment. Peak C, located at 3020 to 3100 cm to the power of -1, is associated with vinylic hydrogens and also signifies an alkene functional group, as it corresponds to the stretching vibration of CH bonds, where hydrogen atoms are bonded to sp2 hybridized carbons in a double bond.
As we can see from the spectra, there are two medium to strong absorption bands in the 3300 to 3500 cm-1 region indicate that N bonding to hash stretching, confirming the presence of a primary amide. Primary amides exhibit two and hash stretching peaks because the nitrogen atom is bound to two hydrogen atoms, and these peaks are often broader due to hydrogen bonding between molecules. For the C and H carbon and hydrogen bonding, absorption band CH observed at 2850 to 2960 centimeter -1 is due to CH stretching of sp3 hybridized carbon atom, which is typical of alkyl chains. For the C double bond O, explanation is strong absorption band at 1650 to 1680 centimeter -1 correspond to the C double bond O stretching of a carbonyl group. This band is intense because the carbonyl bond is highly polar and its stretching result in a significant change in dipole moment.